All right, so we're happy to have Billy Braasch today give us our IQS seminar for the week. Billy did his PhD in Dartmouth in 2020, working on topics in quasi-probabilities and quantum foundations, and then moved to NIST, Maryland, where he's working on topics regarding quantum thermodynamics with Nicole Yunger-Halpern, who is a friend of the Institute and a frequent visitor. So we're happy to have you, Billy, and looking forward to what you have to say about the conserved quantities and how they impact quantum thermodynamics.
Great. Thank you, Andrew. Can everyone hear me okay on Zoom? Good. Yes, so I want to start by thanking Andrew and Justin Dressel for having me here, and Vivek for helping organize my visit. And I also want to mention that I don't think I'd be here if it wasn't for Justin Dressel informing Nicole at some point that a quantity that she was working with is a direct distribution. So that's the story Nicole told me. Yes, so today I'll be talking about what happens to entropy production when conserved quantities fail to commute with each other. And this is work you can find in the archive at this link here. And okay, can you see my mouse moving? Yes, okay. And it's done in collaboration with Twash Upadhyay, Gabriel Landy, and Nicole Yunger-Halpern. And in the back of your mind, what you might have as a prototypical setup for what I'll be discussing is a pair of qubits, and they undergo some unitary interaction such that they exchange angular momentum in the X, Y, and Z directions. And I want to explain this setup in more detail. But first, let's step back go to a more familiar setup and step back into an introductory course in statistical mechanics. All right. So consider two baths, bath A and bath B. Each bath has some particles in it. And let's imagine that bath A has a higher temperature than bath B. So I've denoted more energetic particles with these longer arrows. We'll prepare these two baths in canonical ensembles. So the probability of finding bath A with some energy EA has this Boltzmann distribution, where beta A is an inverse temperature and ZA is the partition function. And there's a similar description for bath B. If we let these two baths interact, some energy is going to flow, and we expect it to flow from bath A to bath B with a higher temperature. And entropy will be produced via this process. We can make it a little bit more complicated and allow the baths to equilibrate with some larger systems by exchanging particles as well. And we'll imagine that bath A has a higher chemical potential than bath B. And we initialize them in grand canonical ensembles. So here in the exponent, we now have another summand with the chemical potential times the particle number in bath A. All right, that gives us the joint probability of finding bath A with this energy and particle number. Again, we can let the energy and particle, the two baths interact, and energy and particle will flow, and we expect entropy to be produced. Because both energy and particles will be globally conserved in these two baths, I'm going to use the term charges to refer to them. Okay, so there are quantum systems that have a very similar setup to what we have here, but we can alter the setup in a very subtle yet radical way. Instead of just allowing the two systems to exchange energy and particles, that these are two observables that commute with each other, we can allow them to exchange some possibly non-commuting quantities. For example, we could consider two qubits that undergo some global unitary interaction such that they exchange angular momentum in the X, Y, and Z directions. So here we have these poly operators. And what I really mean is that when the joint state evolves under the unitary, the average of sigma x in subsystem A is going to be changing from the beginning and the final time. But we don't have angular momentum moving from the x to the y direction in the global system. That's globally conserved. So it's just being shuttled from qubit A to qubit B. You could think of unitaries that do this. So my talk is going to be about how we understand entropy production in this sort of a context, and how that introduces some subtleties.
So
Yes.
just to clarify what you meant by that, do you mean something like sigma x plus sigma x1 plus sigma x2 is conserved?
It commutes with the unitary.
So
Yeah.
some of the
Yeah, exactly. And please ask questions as they come up, and yeah. So after that little introduction, here's an outline for my talk. I'll be continuing to discuss this classical heat flow setup and how entropy production is understood in that venue. And I'll show how there are 3 equal formulae for entropy production that come from different perspectives. Then I'll move on to the quantum setup, and we'll see how noncommuting quantities introduce some difficulties. And using a toolkit known as quasi-probability distributions, I'm going to generalize the 3 formulae that we had in the classical case to the quantum setting, and we'll see that there's a breakdown in the equality of these 3 things when the charges or conserved quantities fail to commute with each other. And I'll explain how each formula leads to some insight into some sense of entropy production in a physical system. For example, one of the definitions of entropy production will become a witness for nonclassicality. Okay, so here's a slide I had before. Now, when I said we expect energy and particles to flow from hot to cold or high chemical potential to low, this is an expectation. This is an average behavior. But if we do this same setup over many trials and let the 2 baths interact with each other, there's going to be some fluctuations around this average. And each trial is going to have what I'm going to call a trajectory. And when I say trajectory, I just mean a bit of a more permissive sense of that word, where instead of being a path through phase space, it's just a set of initial and final values ascribed to some observables. So here I have the initial energies for bath A and B and particle numbers in the 2 baths, transitioning to some final energies and final particle numbers. So each trial has a trajectory like this. For each trajectory, we can associate a stochastic notion of entropy production. And so I've written one equation down here. In the first term, there's a difference in inverse temperatures, and then a difference in the final and the initial energy for subsystem A. We are going to assume the energy is globally conserved by all these processes. So the change in energy in bath A is going to be the negative of the change in energy of bath B. And if you take that fact into account, you can rewrite this first term in this way. And invoking macroscopic thermodynamics, this looks like what you would expect for the entropy, for some energy flowing into a bath. The second term can be rewritten in a similar way, assuming conservation of particle number. So this is a stochastic version of something that's more familiar in macroscopic thermodynamics. And we have I said I'm going to be introducing 3 different formulae. We have some names for these that are our own names. We call this one the charge formula, but these are common formula that people use.
So this is a definition of stochastic entropy production, or
Yeah, this is one that we're defining and calling the charge definition. Yeah, and I'm going to refer to it as sigma charge. Okay. Another formula for stochastic entropy production can be motivated by considering a notion of irreversibility. So these sorts of situations, like an egg cracking, as time evolves forward, is common in our everyday experience. And one way to capture irreversibility is to imagine you're shown a movie of this, either of an egg cracking or of a cracked egg reforming to a whole egg. So in a loose sense, irreversibility is reflected in how confident you are in whether the movie is being played forwards or backwards. For example, if I showed you a movie of a ball being thrown through the air, you wouldn't be able to say with confidence, if I was playing the reel in one way or another. And so this process is reversible. And we can formalize this notion by considering probabilities with which certain events will occur. So if we go back to our setup that we've been talking about previously, the analog of the egg cracking would be energy flowing from hot to cold. And the analog of the cracked egg reforming would be energy flowing in the reverse direction. So we have a trajectory associated with what I'm going to call the forward process, which is the one you'd expect to occur. And associated with this forward trajectory is a reverse trajectory, where now in the forward trajectory started with energies EI and ended with energies EF in the two baths. And the reverse flips those around. Here axes for classical phase space. And the forward trajectory will have some path associated with it, with the initial point determined by some point in phase space associated with these initial energies, and a final point associated with the final energies. And the reverse trajectory will flow backwards, starting from the final position coordinate that the forward one had, but with inverse momentum back to the beginning point. Okay, so we can work towards our equation for stochastic entropy production by considering a ratio of these two probabilities. I said irreversibility is reflected in how confident you are in whether something can be, a movie is being played in one direction or another. And so this confidence you could also make more rigorous by thinking of the probability. If the probability of the forward and the reverse trajectories is equal, then this ratio is going to be 1. Whereas if one has a higher likelihood than the other, you're going to get either a large number greater than 1 or a small number approaching 0. Now, because the system, we're just talking about a classical system here, is going to follow some deterministic flow, these probabilities for the forward trajectory and the reverse trajectory is just determined by sampling the initial point in the phase space. So this is how we get this first equality, where gamma f of 0 just depends on EIA and EIB. And similarly for gamma r of 0. And we know how to calculate those probabilities they're just given by the Boltzmann distribution because of the way that we prepared our two systems. So we can insert these Boltzmann exponentials, and rewriting this equation, we end up, we can bring everything into the exponent. And we see that we have the inverse temperature times the change in energy of system A, and the inverse temperature beta B times the inverse temperature of system B. And I've circled 3 expressions here. And these are going to lead to 3 different notions of stochastic entropy production. If we take the logarithm of the last expression, we end up with the charge definition that I already introduced. Okay, so we take the logarithm. And that also allows for the ratio of the probabilities. We'll end up with an equation that's positive when the forward trajectory has a higher likelihood than the reverse one, and a negative stochastic entropy production when the probability for the reverse is greater. So that it's natural that to distinguish the likelihood of those events by taking the logarithm here. Okay, so we have these three expressions. I already introduced the charge stochastic entropy production formula for classical system. Now, the trajectory, what we call the trajectory stochastic entropy production formula, is given by the natural log of the probability of the forward and the reverse process. And this has also been referred to as the length of times arrow. And I know that Justin Dressel and Andrew Jordan and collaborators have thought about this for continuous measurement setups as well. And then our third definition we call the surprisal definition, and has a more information theoretic flavor. So the surprisal of an outcome of a probability distribution, also known as the information content, is minus the logarithm of that probability. So this final definition tells us how much information we gain if we'd expected initial energies, to find the system with some initial energies, EIA and EIB, but instead we found them with the final energies. So three different perspectives on entropy production lead to these three equations, and they all equal each other in this classical setup. That's the main message from this portion of the talk. So now I want to briefly introduce the notion of fluctuation theorem dealing with stochastic entropy production. And from the trajectory formula that I've written again here, we can derive an equation, sometimes referred to as a Jarzynski equality. And if we take an average of an exponentiated negative stochastic entropy production with respect to the probability distribution over the forward trajectories, we find that this just equals 1. And this fluctuation theorem is a strengthening of the second law of thermodynamics, using Jensen's inequality that encapsulates the convexity of the exponential. This implies that the average entropy production is greater than or equal to 0. So this is a nice result. And because we have these three different definitions that all equal each other, we can plug into this average the charge definitions. That's what I've done here. And since energy is conserved, we can rewrite the change in energy of system B as minus the change in energy of system A. And we end up with this final equation. And this is a statement that heat will always flow from hot to cold on average. So it's really nice that all these things equal each other. Now I'm going to go into the quantum setting, and we'll see how this breaks down. So the quantum setup is very similar to the classical setup. Again, we have these two baths. One has a higher temperature than the other. We prepare them each in canonical states. Now we have the Hamiltonian for system A and the exponent instead of just its energy. But assigning values to observables in classical physics, of course, is much more straightforward because we don't have to worry about measurement disturbance, which we will have to do in quantum mechanics. So let's think operationally about how we access probability distributions that we saw before. So we want to prepare our system in a tensor product state of two different canonical states. And we want to implement some energy conserving unitary U that'll shuttle the energy back and forth. But in order to have a probabilistic notion of the energy flow, we should make some measurements. We should measure the system's energy before and after we implement the unitary. So we can do that. We can access a joint probability distribution for the initial energies in the two baths and the final energies. And that calculation that we went through continues to hold, and we will have equality for the three equations for stochastic entropy production. We could even let particle flow between the two systems, initialize them in grand canonical states, and again, measure these two observables, implement the energy and particle conserving unitaries, and measure the observables again. And because they commute with each other, we can do these simultaneous measurements, leading to a joint probability distribution. And again, we have equality for these definitions of stochastic entropy production. But we want to go into a regime of quantum mechanics that is a bit deeper. We want to consider two baths that, in this case, we'll imagine that they each have three charges, Q1, Q2, and Q3, that don't commute with each other. For example, at the beginning, I gave the prototypical example of two qubits exchanging angular momentum. So we'd like to understand what breaks down in this setting, or we will see that something breaks down. Considering thermodynamic systems with non-commuting charges has been quite popular in a small subgroup of people studying quantum thermodynamics. And along with other groups and other members of Nicole Younger-Halpern's group, we recently wrote a Nature Perspectives article that summarized some of the, all the main results in this field. So if you want to read more about that, you can look there. But just to summarize a few, non-commuting charges validate derivations of the thermal state's form. So the usual way, or a usual way to derive the thermal state is to think about a microcanonical state where observables all have well-defined values. But of course, if charges don't commute, this breaks down. So there had to be some innovations, technical innovations to derive the state's form. There's, in this particular paper, they invoked approximate microcanonical ensemble where all the observables have approximately well-defined values. They also require a new form of the eigenstate thermalization hypothesis. And this is a tool that can be used to explain how quantum systems thermalize, even if they're closed, not interacting with some external environment. And non-commuting charges also can reduce entropy production rates in the linear response regime. And this was, so I want to highlight this third paper because this was really a large part of what motivated us to carry out this particular study. So we asked what happens to entropy production in more general, arbitrarily far from equilibrium scenarios. So first I need to explain what the thermal states are when you have non-commuting charges. So our set of charges will be Q alpha, label them alpha. We have our system, it's going to exchange charges Q alpha with the bath. And in general, the thermal state is called a generalized Gibbs ensemble and takes the same form, exponential form. It's a Boltzmann distribution. And in the exponent, we have a sum over all the charges. And we have some generalized inverse temperatures, beta alpha. and the chart and the observables Q alpha. And this is the state that maximizes the entropy given some constraint on the average of these observables Q alpha. So you could think of the beta alphas as the Lagrange multipliers for that maximization problem. If the charges don't commute, we call this thermal state the non-abelian thermal state. And it takes the same form, but because its derivation is more involved, we highlight this by giving it a new name. And its form was first derived by Jaynes using maximum entropy considerations. And then about 8 years ago, there was some renewed interest in this, and these 3 papers were published. Okay. So now that we have non-commuting charges, how are we going to understand the entropy produced due to their flow? So we generalize our setup to deal with non-commuting charges, and we have these non-abelian thermal states. Just for simplicity, I'm going to say that there are only 3 charges being exchanged, Q1, Q2, and Q3. And the inverse temperatures for all of these charges are going to be, generalized inverse temperatures are going to be different between bath A and bath B. So what if we do the simple-minded thing? We prepare our joint state, we implement some charge conserving unitary, and since we can't measure these charges simultaneously, we sequentially measure each system's charges. If we do that, of course, we can have some well-defined value for one charge, then the second one, but the first one's been disturbed, then the third one. So there's a problem. We don't get this, probabilistic picture of each charge having some well-defined value. And this is because the measurements will dephase the state with respect to the charge's eigenbasis. And the state, rho, has coherences with respect to every charge's eigenbasis. So the outcome of the future measurements will certainly be disturbed. In order to get around this problem, we are going to introduce a mathematical toolkit known as quasi-probabilities. And the idea is that we ended up disturbing the system by making these weak measurements. Well, perhaps we should consider weakly measure each of these charges sequentially. Let me introduce some notation. Here is the eigendecomposition of each charge. So little lambda alpha A indexed by K will be charge Q alpha A's eigenvalue associated with the projector pi, the eigenprojector pi alpha A indexed by K. And we're going to make an assumption that these are rank 1 projectors here for simplicity. I need to introduce one more notational convenience. I'm going to define a bipartite projector, pi alpha, that doesn't have a subsystem label. That is a tensor product of 2 eigenprojectors of charge Q alpha. Okay. If we'd made strong measurements, say of just 2 charges at the initial and final times, then we get a probability distribution for the values of 2 non-commuting charges, let's say. And this probability in quantum mechanics is given by this trace, where you have the initial state rho A tensor rho B that's sandwiched by these projectors, pi 1, projectors onto charge 1's eigenstate labeled with I1. And then we have another sandwich of projectors. It evolves according to the unitary. So this is what we get in the strong measurement case that had this disturbance. If we make many trials of weak measurements, then we can infer a Kirkwood-Dirac quasi-probability. And I write that with a tilde to indicate that it's a quasi-probability. And it looks similar to what we had in the strong measurement case, but now there's only one instance of each eigenprojector. You can kind of start reading from right to left to go through the operational procedures of the experiment. Prepare a row, weekly measure, project onto charge 1, weekly measure, project onto charge 2, evolve, and then do the final measurements. This quasi-probability can be possibly negative or non-real. And but we still call it a quasi-probability because it behaves very similar to probability distributions in the fact that it's properly normalized and its marginals over one index all give probabilities that conform to the Born rule prediction. So if we go to this weak measurement setup, we're led to a framework using quasi-probabilities to describe the flow of the charge. As just a quick example for how one can do calculations using quasi-probabilities, you could calculate the average current for charge Q alpha, and this is just going to be the change in the expectation value of this observable Q alpha A tensor the identity in system B. The change in the expectation value of that from the initial to the final time, which is just what I've written here. And because, so taking the eigen decomposition of this observable, we can rewrite this equation in this way that looks like similar to a probabilistic average of the difference between a final initial value for this observable, but we average with respect to a quasi-probability instead of a probability. So this can be thought of as like the quasi-stochastic current of this charge, or the current in this quasi-probability setup, just to get a flavor of what people do with quasi-probabilities. So Kirkwood-Dirac quasi-probabilities have been used in a number of instances in quantum thermodynamics. There has been a Nicole derived a Jarzynski-like equality or something like that fluctuation theorem I introduced before that applies to something known as the out-of-time order correlator. And this is something that diagnoses scrambling of information or delocalization of information through many-body entanglement. It's also been used to identify non-classical heat flow and derive another type of quantum fluctuation theorem. And there's an overview of its usage in quantum thermodynamics in this paper published in Quantum this year. And there's been some spreading interest in other fields such as quantum metrology, quantum foundations, and condensed matter physics. So now that we have this quasi-probability setup, I want to introduce 3 generalizations of the formulae that I had before, applicable to this quasi-probability framework. So we have the charge stochastic entropy formula for quantum systems. And if you ignore the alpha subscript for a second, what we're summing over looks very similar to the charge definition we had before, where we have like a analog to the change in energy of system in bath A multiplied by the analog of an inverse temperature, and similar for bath B. And then we sum this over all the different charges. The trajectory SEP formula is generalized just by looking at the natural logarithm of the quasi-probabilities associated with the forward and the reverse trajectory instead of the probabilities. So if we had 2 charges, we have a quasi-probability for some initial values and some final values, transitioning some final values over the quasi-probability associated with the reverse process. And the surprisal formula is similarly just given as a ratio of probabilities, but these probabilities are associated just with sampling charge Q alpha and finding that it has some initial values. So there's a bit of a broken symmetry here because we've picked out a specific charge Q alpha for the surprisal formula. And we think of that as being determined by which weak measurement you choose to perform first. But the results that the insight that this leads to doesn't matter on which charge you choose. So these three formulae all equal each other when the charges commute, but when they don't commute, then they all fail to equal. So that's one thing that we found quite interesting. And yeah, so now I'm going to be talking about insights that each one of these formula for stochastic entropy production leads to. Here's the charge formula. I want to introduce a concept that I call a conserving trajectory. So here's some trajectory with initial and final values for charges, for C different charges. And for each charge, if the sum of the initial values in the two subsystems is equal to the final values, then I call this a conserving trajectory. If the quasi-probability, if the charges all commute with each other, then the quasi-probability will only have support on conserving trajectories. However, if we have non-commuting charges, there's actually a non-zero support over the non-conserving trajectories. So in this quasi-probabilistic framework, there's something interesting going on because we still have, on average, there's charges being conserved. Each of the charges is conserved in the two systems, but we can have these quasi-probabilistic trajectories where the charges follow each other. A second insight comes from the surprisal definition, and we can calculate the average of this entropy production. And this is written as the difference between two relative entropies. Here I've written the dephased state in Q alpha's eigenbasis as phi alpha of rho. So since we're preparing the system in a tensor product of these thermal states, if the charges commute, then the dephasing operation will do nothing. And so this term, the second term, will be zero. And due to the non-negativity of the relative entropy, this average is always going to be greater than or equal to zero. However, with non-commuting charges, this average entropy production can become negative, which seems curious, but having a negative average entropy production actually isn't so unfamiliar. It's like we're turning back the arrow of time somehow, or like reforming the egg. And this sort of thing can happen if we access some sort of resource. For example, we could use work to make heat flow from cold to hot. And in this case, we interpret the coherences in the initial state as some resource that we can leverage. From the third definition, the trajectory stochastic entropy formula, we find that this can behave as a nonclassicality witness. So if we average this with respect to the forward quasi-probability, not only can it be negative, but it may not even be real. Right? The physical insight is that it's a non-classicality witness. So how does this work? If we write down the equation, we can plug in the two expressions for these quasi-probabilities. And if we have C different non-commuting charges, we'll have all these projectors. And there's a large cancellation that occurs, allowing us to rewrite this formula in a simpler way. So let me repeat that formula. And this this expression can be rewritten as a ratio of weak values. And I know we have lots of experts on weak values here, but for anyone who hasn't been introduced to them, I'll just give a brief explanation. So imagine that you have prepared your system in some state I, and at some later time, you plan to do a measurement and post-select on some state F. The weak value of some observable O is equal to this expression and can be thought of as the most reasonable value, loosely most reasonable value you might ascribe to this observable at some intermediate time between the preparation and post-selection. And operationally, this weak value is associated with disturbance of a pointer in a pointer system or an ancilla system in a weak measurement setup. Okay, so this definition, like we're thinking about preparing mixed states, not pure states, but the weak value can be generalized to a mixed state preparation. So to learn more about this, it was first introduced in this paper in '88, and there's a nice review by Justin Dressel and others published in 2014. So why do we want to connect this equation to weak values? Well, it's known that when a weak value lies outside of the spectrum of some operator, O, this implies a notion of non-classicality known as contextuality. And this was proved by Matthew Pusey, and I know that Matt Leifer's thought about this a lot too. And there's another paper published in 2019 that shows that not only the real part of the weak value, but a non-zero imaginary part. So a negative real part of a weak value or a non-real weak value can also indicate contextuality in a very specific setup. So what is contextuality for like people who haven't thought about this before? I'll just like briefly sketch what this notion is. I'll be talking about a generalized notion of contextuality introduced by Rob Speckens. And here I'm just talking about contextuality for a specific aspect of an operational procedure for preparations. So let's say you have some number of preparations, these boxes with red buttons that are going to produce a quantum state for you. And you'd like to think of there as being some underlying states of reality, like something akin to a phase space point or some, like the side of a die when you roll it. And there's some state space S with these underlying states of reality, also known as ontic states lambda. And you'd like to think of these preparations as preparing the system, each preparation having some distribution over the ontic states. Let's say you interrogate all the preparations with any measurements you could think of, and you find that 3 of them have the identical statistics. They're operationally indistinguishable. It's a simple explanation for why you can't distinguish them is that, well, they're all preparing the same ontic state with the same probability. So these 3 are operationally distinguishable. They all have the same underlying probability distribution over the ontic states, but this one you can distinguish, so it has a different probability distribution. So this is a very permissive notion of what it means to be classical, and this is known as non-contextuality. Why do we use the word context? Well, no matter what measurement context you interrogate the system with, you are still able to describe all of these preparations with the same distribution. And not only is this a really important foundational concept, but also it's been used to explain why quantum computers have speed ups in certain regimes, like in this paper from 2014. So the non-classicality witness comes from this argument. So if sigma trajectory is not real, then a weak value must be non-real or anomalous, as it's called. And anomalous weak value implies contextuality in the process. Prepare row, weakly measure this eigenprojector of charge Q1, projecting onto state labeled I1, implement the unitary and post-select on this other eigenstate. And this is a version of the thermodynamic process that we were thinking of with weak measurements of all the charges, where you just limited the strength of the measurement of all the charges except for charge 1 to 0. So that's how this connects to that process. It's a specific instance of that. This is one of a few thermodynamic quantities that signal contextuality. And so there is a paper from Amikam Levy and Matteo Lastaglio, where they find a bound on heat flow that can be described in a non-contextual setup. And I think one of the strongest notions of contextuality in quantum thermodynamics is shown in this paper, where the connection is much more direct, where he's showing that work extraction is possible at a rate for quantum systems that's impossible to explain using a non-contextual ontological model. And there's been some experimental work as well. So in summary, I reviewed 3 formulae for stochastic entropy production. In the classical setting, we generalized them for non-commuting charges. And we saw that when charges fail to commute, the formulae fail to equal each other. And really what that is telling me is, like, there's a lot more to learn about what really are these things that I'm all calling stochastic entropy production. I shouldn't all call them the same name because they're all different things. But we saw how they provided different insights into the physics. There's some opportunities for future work. You can take every stochastic thermodynamic phenomena and ask, well, what happens if the dynamics conserve non-commuting charges? So yeah, lots of stuff to be done. Also, thermodynamic uncertainty relations provide a bound on the precision of a current, or the ratio between the variance and the average current that's given by the average entropy production. And so I'd like to learn more about these. And I think by studying other applications, I'm hoping that certain definition might be signaled out as more relevant than another. There's also been some work on looking at quantum engines, where an engine will exchange non-commuting quantities with a bath or multiple baths from a resource theory perspective. And that's quite different from the perspective we've been looking at. And so I'd like to study that because, well, we'd like engines to be more efficient. And so if we can reduce the entropy produced by an engine, that would be a good thing. So finally, I want to thank everyone for your attention. If you want to read more about this work, you can find it on the archive, or about non-commuting charges in general, you can look at this paper. And I want to thank my collaborators, Twesh, Nicole, and Gabriel, and yeah, all of you for your attention. Happy to take questions.
Yeah, I have 2 questions. One is, can you go to the slide where you show the weak value formula and like equated with the, this one.
Oh, Oh, the weak value form.
Yeah, so I was just wondering, so in case of weak values, the interpretation is basically if you're measuring an observable, you prepared as initial state and post-selecting on a final state. But in this case, U is not a Hermitian, it's a unitary operator. Is there some sort of change in interpretation due to that?
Yeah, if you have some unitary evolution, I mean, one way to think about it is to kind of lump that into your pre-selection or post-selection, and just imagine that you're effectively post-selecting on a different state. So if I put a U after the O here, it's like I'm post-selecting on the state U dagger F instead of F.
I had one more question, was that when you introduced the quantum ensembles, e to the power minus beta, summation beta alpha, Q alpha.
Yep.
I was wondering, is there a like, how do you get these states in practice?
Yeah, that's a good question. So in practice, you mean in a lab, in an experiment, and there has been one experimental result that I know of dealing with non-commuting charges, and it was a trapped ion experiment in Rainer Blatt's group in Innsbruck. And so basically they prepare a spin chain. I don't know how many ions they had in it, but the basic question they're asking is, well, can we show that a quantum system that exchanges non-commuting charges actually has some long time state that's close to what is being claimed here, this non-abelian thermal state. And so I don't exactly know how the experiment went, but like 2 of the spins are thought of as the system, and the rest of the spins in the chain are the bath, and they initialize them in some non-equilibrium state, and then allow it to like couple the spins using some Heisenberg interaction. Allows the angular momentum to be exchanged. And they see that in the long time, they get something quite close to the non-abelian thermal state.
So related question. So the Q's here are, I guess, the regular momentum if you're talking about spins, but not energies, or they would be associated with energies using some like magnetic field or something.
Yeah, you could have that as well.
But that's what the Q's would be with the energies.
Yeah.
So I just have a question about these states in general. So do you know what happens, what becomes of the complete passivity derivation of the thermal states in this?
Yeah, I couldn't reproduce it for you off the top of my head, but I know that is another way to end up at this state.
Okay, so you can do it.
Yeah, and so that's actually, I think in this 2016 paper of Nicole's, there's like this three derivations. One is, so Jane's had this information theoretic derivation, but the idea was like, let's actually get the same result by thinking more physically. And so there's one derivation using an approximate microcanonical ensemble argument. There's one that's like complete passivity, resource theory derivation. Yeah.
I have a question.
Yes, please.
So you discussed 3 definitions of entropy using the probabilistic description. So I was wondering, if for a process, is it possible that they give that the second law of thermodynamics is not satisfied for some of those in the case of non-commuting zones?
Is it possible that non-commuting charges can lead to violations of the second law of thermodynamics? Well, beyond, so I did mention, I gave instances where, the average entropy production is, can be less than 0. So I think that is, an answer to your question that yes, it can be violated, but on the other hand, we wanted to have a good explanation for why these sorts of violations could occur. And so I tried to motivate that by explaining that there's something that could be consumed as a resource that is being indicated by this violation of the second law.
So you're basically saying that you're not taking everything into account.
Exactly. I'm not taking everything into account. So I think that's like,
If you were, the second law would be obeyed. That's the
that's my intuition, but I'd be like, if you really
I don't
press
think we
me,
can argue
I'd
that,
have a
right?
hard time saying one way or the other. Yeah.
I wouldn't stake any claim on definitely violent for sure.
Yeah. Yeah.
I mean, why didn't, I mean, probably I missed that, but can you make a similar argument with a thermal bath? I mean, what happens if you have like a thermal bath? You do measurement on, like, let's say you have two systems, you have thermal baths, and you do measurement and you exchange angular momentum between them. Do you have, like, what happens with these three definitions of entropy production? Are they?
Well, I think like that's basically the setup
Right.
that I have. So I'm not quite sure how.
State of
what you're describing
using
is
the, no, I mean, you just need the Gibbs ensemble then, right? You don't need the non.
I see.
Yeah, just like,
I was
I've
thinking
said,
like generalized thermal
right,
states. You're just saying Gibbs ensemble.
right.
And you're asking what would happen if we allowed them to exchange.
Right. You just allow like measurement and all the stuff that you did. Yes.
Mhm. So in that case, it's not obvious to me. I mean, it's like we're kind of taking a state that is a bit more permissive than the initial states I'm thinking of. Right. So you could, engineer all sorts of Hamiltonians that give you your canonical state.
Yeah, but it would be a simpler quantum system, right?
But you're still saying allow it to exchange non-commuting
Yeah,
charges.
exactly. You can say like I have sigma x instead of sigma g, which are in the system.
Yeah. Yeah, I'm not sure what would happen there, but yeah. Sorry.
Can you talk a little more about the non-conserved trajectories? And because it seemed like you were saying that energy was conserved between the initial and final state. Did I miss something there?
Okay, sorry. Where am I going? So this was the slide you're interested in? Yeah, so the conserving trajectory in the quasi-probabilistic framework has the initial values for the charge Q alpha and the two subsystems being equal to the final values. So it's like exchanged at the like microscopic level in the quasi-probability framework. Now, if that's always the case, then on average, it'll also always be the case. But we find that dealing with non-commuting charges, there are actually instances where this is not the case, where you can have a quasi-probabilistic trajectory where there seems to be like more of one charge and less of another, let's say. But if you take the average, the quasi-probabilistic average, you still find that the expectation value of charge Q alpha has not changed. That's what I meant to say.
So on a case-by-case basis, you have two systems that are coupled and quantities that they share are not conserved. That's what's happening here. But if you average, they'll be conserved on average.
In the quasi-probabilistic framework.
If you average with those
probabilities. Yeah. So, okay, since we're dealing with quasi-probabilities, you run into the issue of saying like, well, what's really going on behind the scene? Okay, we're dealing with quasi-probabilities. So, yeah, we don't I'm not saying that some of this charge is coming from nowhere because we're working in a quasi-probability framework. But I am saying that this is something unique that happens when you have non-commuting charges, and maybe there's something more to be learned there.
Any questions about Zoom?
I'd like to make a comment. So I think the most natural realization of these charges is in fact energy, where you replace the charge with a Hamiltonian of a system, and the other charge is, for example, a coupling Hamiltonian or something like that. And there's a large literature that looks at exactly these same questions and is trying to understand where energy comes from, especially when you do things like post-selection, right? Or looking at case by case questions about, is this Q conserved or not, right? And so I strongly argue in those cases where you seemingly see non-conservation of the charges, the answer to that is not, as you say, it's not because charge is being created out of nowhere. It's because there's uncertainty in the original distribution of the charges. And so you can pin that non-conservation on the fact that you don't know exactly what charge you started with because you have some ambiguity with that. And so I think that's one way of explaining it. But the other point I wanted to make is that exactly this point of non-commutation of Hamiltonians, particularly for energy, underlies this body of work that I've been involved with about quantum measurement engines. Because you have to measure the system in some basis that does not commute with the Hamiltonian of the system. And when you do that, you show that you exchange energy between the system and the measuring device. And then you can use that as the kind of a source of energy to drive the engine. So I think those exactly those same points you're dealing with come up in that paper. And we also look at, for example, entropy-production in those papers as well. That would be something to look further into.
Oh, thank you. Do you think that dealing with non-commuting charges will somehow allow you to extract more energy, beyond just making measurements outside of the energy eigenbasis?
Well, indeed, for these measurement engines, that's the only way you can extract energy. Because if you measure in the eigenbasis so that they do commute, then there's no net transfer of energy. You can think about it as just revealing the energy uncertainty that's already there. Whereas when you introduce non-commutation, then you can show that you get either gain or loss of energy from exchange between the systems. And then by looking at the result, then you can then act selectively to be able to extract that energy. So that's a key feature of how those measurement engines work.
I'd really like to learn more about that. So I'll definitely look up those papers.
Great. Yeah, and of course, our grandfather of the Institute, Yakir Aharonov, raised this same issue, I think in 1980 or something like that, with his gamma ray paradox. It's exactly the same kind of thing that he thought of decades ago.
Oh, really? Wow. Thanks for the references. I appreciate it.
Yeah. Okay, thanks for the talk.
Thank you all for coming.
So thank you.